The recording. Okay. So good afternoon, everyone. Today we have one of our own students, Zaid, who is a PhD candidate at Robotics and Mechatronics Laboratory in our Department of Mechanical Engineering at Koç University. He received his BS and MS degrees in Mechanical Engineering from the Mustafa Syria University in Baghdad in 22 and 27. And his research interests mainly include haptics, physical human X interaction, and robotics. And today he will talk about their recent work on employing haptic features for distinguishing between interactive behavior patterns. Okay, thank you, Zaid. The stage is yours.
Thank you, Prof, for introducing me. Thank you all for attending my presentation. Today, I'm going to present my published work, a novel haptic feature set for the classification of interactive motor behaviors in collaborative object transfer. This work has been done under supervision of Professor Çağatay Bajdogan and Professor Ayşe Küçükyıldız. The new generation robots, in contrast to the old generation, are expected to work or cooperate with humans in different environments, like in hospitals, as in rehabilitation application, where the robot has to provide a guidance to human, in industries, as in assembling task, where the robot has to understand the human intention, in home environments, as in transporting an object from one place to another, where some interaction patterns emerge, and the robot has to understand them. Another application is hand over an object, where the robot should know when to grasp or leave the object, and even a restaurant, why not, where the robots serve the customers. The application that we are more focused on in our study is object transportation, where robots can work side by side with a human to manipulate an object from one position to another safely and without having a conflict or endangering the human partner. This collaboration immerses some interaction patterns between the human partner and the robot partner. And this interaction pattern has to be known by the robot to act accordingly. In order to have such a robot, we trust that understanding of physical human-human interaction is crucial to implement a robotic system that is able to classify dyadic interactive behaviors. Humans are sensitive to interaction behaviors during joint action. They can leverage haptic cues to easily distinguish between interaction status, such as harmony and conflict. Therefore, we hypothesize that haptic information plays an inherently important role in differentiating between distinct interaction behavior classes during the cooperation of two physically linked partners. So based on that, our initial focus was to understand how two humans interact, which I'm going to talk about today, but our long-term objective is to program a robot partner that reads the interaction status and reactively acts in response to the predicted behaviors. In summary, our research objective is to investigate human-human interaction and learn from that and do the same with the human-robot interaction. Our experiments. In order to enable two humans to cooperate together to manipulate an object from one position to another, we have designed and manufactured a plexiglass object, as you can see here. It has a dimension of 30 by 20 by 10 centimeters, and it weighs around 2.5 kilograms. Two aluminum handles, each weighing 231 grams, were attached to facing sides of the object to enable the humans to handle it. These handles were attached to the object by two force sensors, and they were used to record the haptic informations, I mean the forces and torques, exerted by the partners. Moreover, we have defined 4 different interactive behaviors that were more encountered during our earlier human-human work, and we believe that they are more come across during the manipulation. They are harmonious translation, HT, where the partners agree on translating the objects toward the common target configuration. conflicting translation, CT, the diode faces a conflict as only one of the partners intend to translate the object to the target configuration. And harmonious rotation, here the partners share the same rotation intention, hence they rotate the object cooperatively. And finally, the conflicting rotation, where the diode faces a conflict as only one of the partners intends to rotate the object. Now, in order to have these interactive patterns during the cooperation between two humans, we have artificially designed 6 different scenarios, where in each of them, the partners cooperate to manipulate an object from one position to another position through executing different submovements. Each of these 6 scenarios aims at isolating more than one of the 4 specific interaction patterns. As you can see here, we have 2 partners. The first one we called the experimenter, the green guy here, and he was given a script of 6 different scenarios, and he acts as a supervisor in our experiment. While the second partner is the subject, the blue guy here, and his given task was always constant. By doing this, we artificially created harmonious and conflicting behaviors, since the partners have the same sub-movements in some cases and different sub-movements in others. It's worth to mention that the subjects were informed that if they feel any conflict with the experimenter, they should leave the subjects or the sub-movements and proceed to the next one. And to make the things clear, I'm going to take this scenario number 4 here as an example to do the animation on it. The subject, as I mentioned, the subject has always the same scenario and hence the same sub-movements. These sub-movements are rotate the object counterclockwise, then translated it to the red point, and then translated it again to the black point, and then finally rotated it clockwise. On the other hand, the experimental 4th scenario includes translating the object directly to this red point and park there. Because of this divergence between the experimenter and subject scenarios, they will have different interaction patterns. As we can see here when we execute the task. For example, here, at the beginning of the task, the subject tries to rotate the object while the experimental doesn't want to do that, so he would apply an opposite torque to prevent that. At this case, we have conflicting in rotation. Since the subjects feel some kind of conflict, he will skip this sub-movement and go to the next one, which is the translation part. Since now both of them want to translate the object, they will harmoniously cooperate to translate it to the red point. Now, the next sub-movement for the subject is to translate the object again to the black point, while the experimental want to park here. So they're gonna have another kind of conflict, which is the conflicting in translation. 12 subjects did the experiment where each of them did 6 scenarios twice. All the data were collected and based on the haptic and position signals categorized into the 4 interaction patterns that we have mentioned before. Now, in order to use these raw haptic data, the forces and torques, to classify the interactive behaviors, we utilized haptic matrices introduced by Nuh and Zafran to quantify the cooperativeness of 2 partners in 1D task. These matrices were introduced based on the following decomposition. If we have 2 partners that apply forces, in our cases, they are the experimental here, the green one, and the subject here, the blue one. So we would have F sum, which is the summation forces of their applied forces. By doing this, any forces aligned with this F sum will be considered the effective forces for that partner. For example, here is the effective forces for the experimenter, and here is the effective forces for the subject. Note that star here refers to effective force. Any other forces that is perpendicular to this F sum will cancel by each other. By doing this, we would have F effective for the subject, which is alpha F sum for the experimental F sum, and another effective force for the subject, which is beta f sub. Note that alpha plus beta is always 1. Based on this decomposition, they have introduced the following force-based matrices. Individual efficiency, and since we have 2 partners in the task, so we would have 2 individual efficiencies, one for the experimenter and one for the subject. Also, they have introduced team efficiency, negotiation efficiency, and similarity. For example, the similarity measures how similar forces they are applied. So if they applied similar forces, similar amount in similar direction, the similarity will be 1. Otherwise, if they apply forces in opposite direction, the similarity between them will be 0. Now, before utilizing these matrices as our feature, we thought that having an observation regarding the forces and torques patterns in the interaction behaviors would help us to understand these behaviors more. Therefore, for instance here, I plot the haptic data, forces and torques, for a representative subject in 2 scenarios. Scenario number 4, the first column, and scenario number 5 in this column. As you can see, A is the applied forces, represent the applied forces by the partners. B, plot the total torques for the applied by each partner, and C is the net torques on the objects. After the investigation, after we investigate the haptic data and these plots for all the subjects in all scenarios, we have 3 suggestions or 3 things to do. The first one is that the applied forces, or 3 notice. The first one is that the applied forces in the x direction and also the applied torques about y-axis, it's worth to mention that x-axis represent the lifting axis for the object and y-axis is the axis of the direction of the motion. So these forces and torques applied in these directions are using mainly to compensate the object weight. So going back to this graph, as we can see here, this is the x-axis, x forces, and here is the y torques. As you can see, through all the behaviors that we have, they have almost the same behavior or the same pattern. So these forces and torques have the almost constant patterns throughout all the interaction behaviors. So they are not much informative, and they might be dominant over other forces and torques applied in other directions. And since their values are much higher. The second observation is that in some behaviors, some behaviors can be seen utilizing the forces rather than torques, while some other behaviors can be seen utilizing torques other than force. For example, here, the conflicting translation, here the subject tries to translate the objects in the direction of z, positive z, so he applied the forces in the positive z direction, while the experimental doesn't want to move, so he would apply an opposite force. This behavior is very observable using the forces. On the other hand, we can see in conflicting rotation, the behavior is more observable using torque. Therefore, based on the first observation, we decided to integrate the force and torque information, and we called it range, which is essential to describe better the behavior pattern. As you can see here in this table, we introduced torque-based matrices to be used as features along with the force-based matrices. So here is the force, the original force matrices, and here is what we have introduced along with the force related to the torque. So notice that the superscript F and tau are used for force and torque respectively, and subscripts here are used for the matrices name. Based on the second observation, we have made that some forces and torques might be dominant and affect other forces and torques, despite that they are not much informative. We decided to do the decomposition and feature extraction in 2 ways. The first one, which is in a 3D dimension, which we call the space-based range or space-based method, while in the second one, we did the decomposition in each plane separately, like in XY, in YZ, and in XZ. Based on this, we have 10 features, in using the first method, the space-based, 5 for force and 5 for torque. while in plane-based we have 30 features, 10 for each plane. Result and discussion. Now, before going into the result, I just want to say that we have now SBW range feature, which is space-based range feature, and the feature here are 10 force and torque related, computed using a space-based decomposition approach, and PBW, where feature set are extracted using 30 force and torque related matrices computed using plane-based decomposition approach. The third observation that we have made that the interaction behaviors generate complex force and torque patterns. And in order to use these haptic data to be used and to differentiate the interaction patterns, we thought that machine learning is needed. So we used random forest classifier. Since we have two feature sets, we trained two classifiers. Before going to the result of the training, I want to explain the method that we trained the classifier based on it. Since we have 12 subjects, and in order to avoid overfitting, we have divided the data, haptic data, into two parts. The first part coming from 8 trials from all the subjects. And this part of the data, this set was used to train the classifier. And the remaining 4 trials for each subject were reserved to testing the resulted classifier. By doing this, we can make sure that the data used for the test have been never seen in the training part. As you can see, we have trained two classifiers, one for SBW feature set and the other one for PBW feature set. Both of them achieve a good classification rate, but still the one trained with the PBW plane-based range feature set achieve a better classification rate, as you can see here, regarding, for example, here in harmonious rotation, it was 65%. Here we jumped to 81, and here it was 76, and we jumped to 100%. Now, since we know that the classifier trained with PBW feature set was better, we want to check the robustness of our classifier. So we used leave one out protocol. So in doing that, we did the following. We take the data for 11 subjects as a training, and then we evaluated the classifier with the data coming from the subjects number 12. So by doing this, we can make sure that this data have been never seen, or this new coming data have been never seen either in training or in testing. We did this for all the 12 subjects. And as you can see here, this is the average confusion matrix for all the confusion matrices or matrices. And it proved that our classifier is still valid if we introduce a new data. After we did that, we showed that the haptic conformation alone, which was the basic output from this work, that the haptic conformation alone was sufficient to differentiate between the interaction patterns. By doing this, we don't have to track any object or to track the position of the object to know about what's going on. So we don't need to track any object, and this will make the manipulation process, even if it was mass production, it would be like much faster. The second conclusion that analyzing the experimental data using different movement planes was more effective to recognize interaction patterns than analyzing the same data, especially in 3D. Thank you for your listening, and I'm ready if you have any questions.
Thank you, Zaid. So I have a question, but maybe I can first ask our audience whether they have any other question. Zaid, I have this question. So here you basically identified certain patterns, right?
Yes.
So I suppose you can you use this framework also to predict some future interactions. Like there could be some uncertainty, but after getting this haptic features, maybe you can decide what are the possible next actions that either the robot or the human can take. So is it possible to extend this to such a formulation, or does it make sense? Because
No,
like if you show, I think you showed this different patterns that we can basically identify a certain structure. Maybe the model can also learn this sequential structure, and then like having this forward model to have also some sense about the possible future actions.
Maybe we can like predict, but very short, like in very short periodic, like for example, if we take the last 50 or
actually that will be my next question. If yes, maybe there is a certain limit, like
exactly.
Yeah.
Exactly. Yeah, I think there will be like a certain limit for that, because the estimation here or the prediction here will be based on the like past data, not from the So you can like, for example, if you can measure what was going on in the, for example, 50 or 100 millisecond before, you can anticipate or expect what would be the behavior in the maybe 5 next milliseconds.
But since you said that, especially in some conditions, this could be quite dangerous for the humans and the robots to work together, even having this property could be quite useful, I guess.
Especially if we can use the matrices to optimize the interaction. So if we can do that, maybe we can extend the expectation from this. For example, if we have harmonious translation for now, for example, so we are in harmonious translation period, but it's not 100% perfect harmoniously. They are not 100% harmoniously translate to the robot, I mean. So we can maybe, based on the indices that we have, we can optimize this translation. And by doing this, if we arise it from, for example, 70% to 100% perfect translation, harmonious, so we can predict that the next 10 milliseconds will at least go on and through the harmonious translation period. I don't know, maybe it's like an open research for now, or we can be like next work.
And can you go to this confusion matrices?
Yeah, sure.
So I think there's this special class that is especially difficult to predict. Right? Like this HT can confuse with HR, right?
HT confusion with HR, yeah.
So is it something that you expect?
Actually, after revising or make the observation about the forces and the behaviors throughout all the interaction or the interaction behavior through the experiment, yeah, we expected that, because the behaviors of the humans during the harmonious translation, for example, and harmonious, throughout all the behavior that we have was very complex. For example, in harmonious translation, sometimes they would exerted the same direction forces to translate the object, but sometimes because of the delay from one subject or other, they would apply different direction forces, although they are harmoniously cooperate to translate the object. So because of this human behaviors, it was expected to have this kind of confusion between them.
I just want to add it something like, so I could tell you like, so by just looking at, Zaid mentioned a little bit, but by just looking at the pure signals like force and torque signals, it is not really possible to understand what kind of interaction they are doing. Like a simple example is, let's say two people are pulling, they are holding an object and pulling from both sides, right? The object is not moving. You think that they are holding in a harmonious way. Actually, like they are like applying opposite forces. So they have contradicting with each other. Or let's say the same two people are applying side forces, right? Tangential forces. Are they intending to rotate the object or are they intending to go sideways? You understand what I mean? Like just looking at the signals is not possible to understand what the interaction is. And in our previous studies, we've been including object-related parameters such as velocity. You can include position because then it will be application dependent. With the velocity, you get really good results, but then we thought that maybe we can come up a bit more sophisticated force tools and force and torque tools so that we can understand interaction patterns. I mean, the key thing is in here is not really instantaneous things. We're paying more attention to overall behavior, what he intends to do, like what is not the what is the, it's not, our aim is not like what's going to be the force in the next step. What is the intention of the user? Is it trying to, you know, harmoniously work with the other side or like conflicting with the other side? So that's the key thing in here. And signals like by itself is not really telling you this information. So you need more sophisticated measures. That's one thing. Another, like coming back to your question, like how we can program the robots, that's still we're working on it. It's not easy. But hopefully like this metrics, like he introduced several different metrics like negotiation metric, like similarity metric. Those maybe can be also utilized to see like how the robot can be programmed. Like if there, it seems like negotiation is high, then maybe robot can be forced to comply with the user kind of thing. But still like this area is open, how we can program, how we can take this work and directly implement it to the robots. We're still working on it. We have some ideas, but we're still working on it basically. Because as I told you, it's not an instantaneous thing that we're looking. So we expect that the robot understand the human intention and then somehow define a trajectory accordingly.
Yeah, exactly. Yeah, this is a really hard problem indeed. Yeah. There is a recent surge in interest in like, can we model theory of mind with these artificial intelligence, just to agents build the state of the other mind, and here you are exactly
close to those
accomplish.
Yes, related to the theory of mind. Yes, very good point.
Okay, maybe we can get some questions from our silent audience. So do you have?
Actually, I want to add something here that when we say we introduced the torque-based matrices, and the Professor Chatai, remember that, we did this classification using either forces, only forces, or torques. And based on our observation, we expected something that by doing this, we prove our expectation that neither forces alone or torques alone can differentiate 100% or at least these four different interactive behaviors alone. So by introducing torques along with the forces, we could achieve that because some related to our observation, some behaviors cannot be seen using only forces, and vice versa. And regarding the open research right now, we are working with Professor Chatai on programming a robot. Actually, we have reached some points, but we are still haven't did the experimental work. So hoping that in the next 2 months or something that we can come back to Turkey and do something regarding this.
Another thing I want to mention is like typically in the student presentation, I ask them to keep it short so that we can have more questions. I mean, there are a lot of details that Zaid hid from the audience, but feel free to ask questions. That's why he's here. He has additional slides and he's ready to answer to those questions. So the graduate students, if you have like, feel free, like you don't have to perfectly understand all the details. That's why we are meeting in here, get some feedback. So go ahead and ask if you have any questions to Zaid.
Exactly. From a more machine learning perspective, I think here, like you should be maybe using some machine learning techniques that also consider the uncertainty in the data, because like I think this is super ambiguous, like you said, from these forces. So that's like one comment I can make, and the other could be, so here you basically use this fixed set of features, but the setting is not online, right? Or
Yes.
is it?
No, it's not.
So maybe it's also could be interesting to work in an online setting, like there's this stream of force features you receive, and from that you start to just try to predict the intention, as Çağatay Hoca has put earlier.
So how can we add the uncertainty? I put in here, he's using random.
So
of course, he's doing post-processing, but when we try to integrate this to the robot, we won't be able to have the whole data. We will have a stream of data. And of course, the buffer size will be a factor, or the method that we are using will be a factor. So how can we add some uncertainties into
So I think Çağatay Hocam, people are mostly using Gaussian processes and I'm not an expert, but like I think that's one of the basic tools.
Yeah. It's the basic tool in signal conditioning, signal. I mean, we know like signal theory. Yeah. Okay, got it.
Okay.
Yeah, it's the main tool in signal detection theory as well, Gaussian.
Well, there are also these deep learning versions as well, like neural Gaussian processes.
One thing that we encounter, like this pHRI, like physical human robot interaction studies, is like the thing is like, since the robot is running the loop at a very high speed, since you are doing a physical interaction, the robot should be, the control loop of the robot should be running at very high speed, like around 250 hertz or more than 200 hertz, let's say. So like in 200 hertz, it's like getting data, updating the forces and things like that. So we really need like tools that can run in almost real time. So we have very little time left.
I see.
We have 5 milliseconds to make a decision. I mean, so that's one of the challenges we have. Like even if we use some kind of deep learning techniques, we have, for example, a recent study on like subtask identification. We have to keep the network small. I mean, if we keep the network larger, we can do it much better recognition or detection, you know, intent detection, but then it's not running in real time. So I'm just wondering, like, if you have any ideas on that, like how to, you know, how to implement more powerful techniques in computational efficient manner. We are open to discussions on those as well.
Yeah, actually, that's also my question. I would really like to know what's generally the best way to do the time series multi-class classification in the very high speed. That's actually a bottleneck in pHRI because you're running the robots in a very, very high frequency. See, that's the intuition of physical interaction, because you always get some feedbacks and the force is generally being transferred. The force data is in a high frequency in a sense. So since we want to judge based on anything kinematic, let's say, kinematic and kinetic, always this judgment has to be done in a very, very high speed. And if you want to go ahead with some machine learning algorithm, then actually also I really like to, I'm working with Professor Washikan as well. So we really like to know if you have any suggestions for high speed time series data multi-class classification. For example, we have 12 channels of signal, whatever it is. Let's forget about the essence of signal. 12 channels of signal, and we want to know that, for example, what's the fastest way to do some time series multi-class classification and prediction? What's the fastest way? LSTMs right now, ANNs, that's what we use, but in any case, I don't know really. I'm looking for advice.
Computationally more expensive, right, Aliza? Isn't that the case?
Yeah, LSTM, of course, because it's connected through each other and it's very hard to go ahead with it. That's why right now we are using ANNs. We are happy with our results, but I don't know, since maybe the researchers present in this meeting are maybe studying the cutting edge in the area of machine learning. I don't know. I really want to hear if anyone knows anything
Not only
about
the speed, we also have like constraints in terms of buffer, like because we have to collect certain amount of data and make a decision kind of thing.
Yeah, exactly. So, data collection, processing, decision making, and also implement it to the real-time controller, which cannot be slower than 500 hertz or something. Right. So that's the bottleneck, really.
Yeah.
So again, time series analysis is not my expertise, but maybe you can check this neural Gaussian processes. Like it also includes this extra modeling of uncertainty, so that might basically help. But I see the main bottleneck here. Yeah.
Yeah.
Neuro
Gaussian, like this is, I know.
Yeah,
Gaussian,
that's the that basically. Let me check whether I can find. So I can maybe send you later. So they basically use this Gaussian process framework, and the network part just approximates the underlying function.
So the network is doing a time series multi-class classification, basically? Is it
so they apply this on time series data, but maybe it, I don't know about the efficiency, of course.
I see.
Actually, recurrent neural networks share weights across time, so they can have they can afford to be much smaller than ANNs. The ANN that we used in our previous study had like 5 hidden layers, 75 units on each. But with an LSTM, maybe that can be done on a single LSTM layer with, I don't know, 30 or 60 cells. And that's why recurrent neural networks were invented in the first place, because they have parameter sharing across time. So the number of parameters it's repetitive, so we have less parameters. So the network can be smaller than the equivalent multi-layer perceptron with the same performance. So it might be worth looking at. Training can be harder for LSTMs. Backpropagation through time might take longer or something, but they can be smaller than ANNs and have the same performance sometimes.
Thank you.
Okay. Any other question, comment? So yeah, if not, maybe we can stop here. So we can stop the recording.